So in other words, this is same as that you take your xt and compute its integral with respect to yt. Okay, so if this would be the only term, then there is no difference between both, but there is another term which we call the correction term actually. And how do you get that correction term? The correction term is that when you integrate a to b dxt, the product of dy dt. Okay, dxt dy. So if you want to integrate a process xt with respect to dt, then you need to do what? Simply integrate xt with respect to dyt. Okay, xt and dyt are equal processes, and then compute the integral of dxt with respect to dyt. This is going to be a deterministic integral. I mean, think about it. So if xt and yt are equal processes, so in this product, which terms are going to survive? The only Brownian motion terms are going to survive. Okay, and since you're going to have a dwt factor, so that will become dt. So this is really a Riemann integral. Riemann integral of the products of the diffusions of xt and yt. Okay. So that's the definition of it. So let's be more explicit. Imagine my xt goes like this actually. So imagine, let me write it in differential form. My xt satisfies this actually. So f of t dt plus g of t dwt, let's call it fx and gx, and my dyt is going to be f dt plus gyt dwt. Okay, so imagine that my x and y are equal processes of this format. So what could be the explicit meaning of this? That's what I would like to know it. So the explicit meaning of this is going to be that you need to substitute your dyt here, okay, and you need to substitute your dxt and dyt here, and then you will see that this process is also an Ito process, so it has some drift plus some diffusion actually. So what would be the drift of this term actually? So what would be xt Stratonovich, integral of Stratonovich integral of xt with respect to yt? So it's going to be what? So xt fy of t dt, right? Okay. So a to b xt fy of t dt, right? G.
y of t.
Yeah.
ये y नहीं आएगा इंटीग्रल के.
नहीं. This is just a product.
यहाँ पे नहीं.
Depend to the dt or
And I'm just substituting the value of dy. So if you substitute the value of dy, what are you going to get?
सही.
So the first thing is going to be st dft
सही.
plus an stochastic integral a to b xt, the drift of the process y dwt plus 1/2 of a to b. So what would be dxt dyt?
gx and dy.
So only these two terms will survive. So it's going to be gx of t, gy of t, and d. Okay. So finally, the integral is going to have the drift that is equal to xt, okay,
addition for the dt
y of t plus gx of t gy of t dt, right? And plus 1/2 and plus it be xt dy of t and dw. So this would be really the explicit meaning of integrating one Ito process in the terms of the other Ito process actually. Okay?
first term fy
You can also, what would be the differential form of it? So imagine that I want to write the differential of J.
ऊपर एक f होगा ना, f y of t dt के साथ जो लिखा है.
Yes.
xt times.
So this must be fy. Right, thank you. So you're gonna have this actually. Okay. Okay. So if you want to write this in differential form, the definition of this Stratonovich integral in differential form, so what it would be? In differential form, okay, differential form, what would be the integral? So it's going to be xt Stratonovich dy t equal to, okay, it's going to be xt dy t plus 1/2 dxt dy. This would be the differential form. And you can also write it as, I mean, if you know the xt and dyt, you can also write this more explicitly as what? For example, xt fy of t plus gx of t gy of t by 1/2, okay, dt plus xt gy of t dw. xt gy of t dw, right? So this would be the differential form of Stratonovich actually. So let's do one example of the Stratonovich integral. This would be one example of it. So let's compute the Stratonovich integral of e to the wt with respect to dwt. Okay. So what it would be? You can write it as directly, I mean, if you write it as, for example, in differential form, I mean, you can compute it in differential form and then write it in integral form. That could be one of the things. So that e to the wt Stratonovich with dwt is going to be equal to what? E to the differential of e to the wt, e to the wt dwt, okay, plus 1/2 of differential of e to the wt and dwt. This is what it is going to be. Okay. This term, in other words, the term that makes these two guys different is this actually. So we call this as a correction term. Okay. Why we need the Stratonovich integral? There are various reasons. Okay. Mention some, but let's compute it first actually. So what would be this? So I can apply Ito lemma here and compute this differential and then substitute value here and simplify it. Okay? So what would be, the expression for e to the this actually. Okay, so it's going to be e to the wt, twt plus 1/2. So you need to apply simple e to lemma, right? The simplest one. So it's going to be e to the wt, dwt plus 1/2 e the wt and dt dwt, right? So what was the simplest version of e to lemma? Remember? Anyone? So the d of f of wt dt is equal to
F prime.
f prime f double prime
What?
1/2 of f double prime of bt pt, but dwt dt plus what was it?
F prime
Plus f prime of
wt
dwt.
right?
Yes.
So this is what really is going to be. So I just applied this to get this. And so what would be the end result? The end result would be that this term will go away. Okay? And the only thing that is going to remain is this 1/2 e to the
wt dt.
wt dt plus e to the wt and dwt. Okay, so this is going to be the Stratonovich of the e to the wt with respect to dwt. ठीक है? Okay.
Simplest way.
ठीक है जी. So that would be really the result, and then you just write it in integral form and you're going to get this. This is where. So see, even if you have an Stratonovich of a process with another process, so the expression that we have driven is that Stratonovich is again going to be an Ito process actually. So it's going to be an Ito process. So the Stratonovich, derivative in the Stratonovich integral and Ito integrals are related with each other actually. Okay, so if you have something in integral form, you can write it into the Stratonovich form, and you can do other way around as well. Okay. Now, let me quickly, just quickly, return to the form actually, something that I wrote previously, just show you that why this really makes sense. So remember, we wrote one SD of this form, 1/2 of b of xt, b prime of xt, dt plus, what was it? No. This form. क्या थी? Second last जो लिखी थी, second last alpha of b of xt plus 1/2, right? Of b of xt, b prime of xt, dt plus
d of xt dwt.
right? And then I said that you can write it in Stratonovich form, and now you can see that how can I write it in Stratonovich form actually. Because the first term is going to be alpha b of xt dt plus, if you combine these two terms, this is really b of xt's Stratonovich with the dw. That's what I was saying. Now you can see that is really the Stratonovich of following is making sense of it? Alright. This bit is important, at least you should have, if you're doing a course on stochastic calculus, you should have Stratonovich type differential equation. I'm going to say that's a stochastic differential equation driven by Stratonovich lines, multiplicative Stratonovich lines. Okay. So the norm to say that I have a stochastic differential equation driven by Brownian motion. Okay. So it means that I have a stochastic differential equation in which the noise is Brownian motion. So you can also say I have a stochastic differential equation that is driven by Brownian motion of multiplicative noise actually, some multiplicative type actually. So I have a so you have Brownian motion, but the noise that you have in it is multiplicative. In other words, some process is multiplied with it. Okay, so this is what the terminology means. So I was saying that that's an SDE driven by what do you call Stratonovich noise. By saying that driven by some noise means that you have that specific kind of noise in your equation. Okay. So now I'm heading towards theorem, which is one of the pivotal theorem in entire stochastic calculus. And this theorem is called the Girsanov theorem. Okay. So I will do a sketch of it. But before that, I have to do some preparation.
Sir,
जी.
Stratonovich की ज़रूरत क्यों पड़ती है?
Yes, sir. For example, let me tell you that why we need a Stratonovich lines. For example, when I was solving one of my problem actually. So in geometry, this is very useful actually. Okay. So one of the problems that I was solving, for example, during my PhD was this actually. That imagine you have a sphere in Hilbert manifold actually. Okay? So it's a sphere in Hilbert space. And imagine you have a particle, okay, who's starting its motion from sphere, which start to move from the sphere actually. Okay? And one of the questions that I studied was that what should be the conditions under which we can say that this particle that has started motion from sphere will always stick on sphere actually. So it will never leave the sphere. So it's like it's like glued with this motion is glued with it. So it's like car, for example. Just think about it. So you take some vehicle, okay? So the vehicle is running on a road. So the vehicle is never going to leave the road actually. So what I did actually was that, if you start your motion from manifold, under what condition you will always stay on manifold actually. So I studied it. And in that, first we studied the deterministic problem. So imagine that this particle is moving in a deterministic fashion on a, on the manifold. And then we studied the stochastic version of it, that now imagine that the particle is moving, but the particle is jiggling actually. So what should be the conditions under that you can, your particle always stick with the manifold actually, okay? So when we were, for example, trying to have this invariance result, okay, we were having a hard time if we were adding, for example, randomness only Brownian motion actually. Okay, so in other words, in my equation, that was, something like this. So the partial u by partial t, some nonlinearity plus the Brownian motion. So if I assume that my particle satisfies this kind of dynamics, then I was not able to get the invariance property. But then I realized that if I replace this noise with some Stratonovich noise actually, okay, so I replace this with some Stratonovich noise actually, then I can get the invariance actually. So I used Stratonovich noise to prove that my particle is always going to stay on the manifold if it starts its motion from the manifold actually. Okay. While with the only Brownian motion, it was not possible. So in geometry, in a lot of geometry, stochastic geometry problem, Stratonovich noise is very useful. It's useful. So why I just mentioned it, though I haven't done anything significant about this, that at least you should have heard of it actually. This shouldn't be a new word for you when you are encountering Stratonovich noise actually. Okay. So it's a very useful noise. Very useful noise.
सर इनवेरियंस की मतलब वही है कि मैनिफोल्ड में ही रहे.
Manifold में ही. That's what. So in other words, if you take your initial conditions from manifold, the trajectory would stay in manifold actually. Okay. So the work that I have given to Fatah is that I did it for sphere. Can you think of it for the torus actually? So what if my manifold is a torus and I'm starting my motion from, for example, torus? So what should be done so that I can stay on torus actually? So we want to do at least for the deterministic case. That's what it's going to be. So obviously one of the challenge become that, I'm saying that, so if u naught is from manifold, the u of t would also stay on manifold, okay? So the first thing would be, does u of t exist in the first place actually? Does u of t would exist in the first place? Because then I will check that, okay, where it lives. Okay, so you need to solve two problems actually. The first is that, okay, the problem that you have, you need to prove the well-posedness of it. Okay. And then, you need to prove the invariance actually. I did it both in deterministic case, in a stochastic case, and then I studied some more properties. Okay. So that's what we are doing. But it's an abstract part, the boring one. That's what I like. Shoshali. So, the next part that I'm going to talk about is to prepare ourselves for a wonderful theorem in stochastic analysis. It's called the Girsanov theorem. So what's a Girsanov theorem? So the rough sketch is this. Imagine I have a process that satisfies some SD. Okay, so it has some drift and diffusion. Okay, so it has some drift and diffusion. Okay. Well, this Brownian motion is defined on some probability space, so omega of p. Okay. Now, one thing for sure is true, that since you have this drift in it, this process cannot be a martingale. So it's not going to be a martingale. Why? So in other words, it could be a martingale because, if you write if you write it in its integral form, so you're going to have this x naught plus the integral of A of s ds 0 to t and b of s dw of s 0 to t. This is going to take this form. Okay. So in general, for an arbitrary A, this process is not a martingale. But I can turn it into a martingale if I can get rid of this term. Think about it. So if you can get rid of this term, you know that it's equal to stochastic integral. And stochastic integral is a martingale. So this would be a martingale. And once you have a process, a martingale, then you have lots of, nice properties about the martingale that you can use actually. For example, in finance, we want to turn things into the martingale because it turns them into, into the fair objects actually. Okay. So you want fairness, you want your market to be rational actually. Okay, so the fair pricing can be done if you turn your things, your financial quantities into the martingale. So for this, what we're going to do, so the Girsanov theorem is a recipe to get rid of the drift from an equation with drift actually. So what we are going to do, we're going to replace this Brownian motion by another Brownian motion actually. But that new Brownian motion is not going to be defined on this space, but it's going to be defined on a new space actually. Okay. But this new space, maybe omega and f are going to stay same. But this new probability measure is going to be equivalent to the p. Okay. And what we will do is that if I'm going to replace this noise in such a way that this term will go away from this term, this expression actually. And hence, your process will become a martingale, not with respect to this Brownian motion, but with respect to that new Brownian motion actually in new probability space. Okay. So roughly, if something is not a martingale, Girsanov theorem gives you a recipe that how you can turn it into a martingale. You need to change the underlying space and you need to introduce a new Brownian motion. That's it. Okay? So this is what the bigger picture is. So my aim would be to, if not rigorously prove it, but at least give you a sketch. But there is a lot of preparation that we have to do, even to mention this theorem actually and to write a proof of it. So I'm going to start with some of the preparations for the Girsanov theorem. Okay? Okay. So this stuff is from this book, chapter 8 actually, so stochastic integration, introduction to stochastic integration. Okay. And even this Stratonovich integral was also. Okay. This was in chapter 7 somewhere. So the stuff that I'm discussing now is in chapter 8 actually. Alright. So let's take a function h that is deterministic for this interval. Okay. Then what do we know about the stochastic integral of this deterministic function? I know about the stochastic integral of this deterministic function is that it's normally distributed with mean 0 and variance as the h2 norm of 2 norm of h actually. Okay. This is really going to be it's a square, right? Not just so it's going to be the square of it. Okay. Alright, keeping in view this fact, I would like to compute the expectation. So I would like to introduce something what you call the exponential process, and this exponential process is going to be an interesting process, which plays an important role.